probability of, you have a random variable that's representing the model. You're trying to find the most likely model. And this model is, and so you're trying to find the most likely, so the most likely model, given that you've observed some data, right? So this is kind of the core question that we're going to be talking about this whole semester. So we're not always going to be using the probability after today. I guess next week will be lectures on concentration of data, but then we'll mainly be looking at it just as some kind of, we'll get some equations that are the end of a probability, but we're motivating this today from the probability perspective. And so we're using so Bayes' rule, and so that meant we could transform this into the probability of the data. So given that we knew the model, times the probability of the model divided by the probability of the data. Okay, so this is what we had talked about, and I'm going to change this slightly to say the probability of the data is given to us, so it's fixed. So we're going to ignore this, right? We're going to say we don't know. It's going to be the same for every model. So we're going to ignore that part. And now it's not exactly equal. We're going to use a different symbol here that looks so that looks kind of like a fish, I guess. And this means proportional to. Okay, so this is going to be term is going to be so proportional to this term. And so the idea of so proportional to is that if you have some function, so g of x that's proportional to another function, so f of x, it means that g of x is going to be equal to f of x. All right. So multiply by a constant. Okay. So and there could be this unknown constant c. It's possible it's known, but the point is that it's not needed to know what this constant is. And so I don't have to specify what the constant is. So I know if I change x and this one goes up, then this one also goes up. Okay, and so just as a shorthand notation I can use here. Okay, and so now I can drop this term in the denominator, which I didn't need anyways. All right. So the other issue is that, okay, so if we're dealing with discrete random variables, right? Like, let's say that in the case with the windshield, there were 3 possible factories. These were the models, and the windshield was either broken or it was not broken. There were discrete cases. Then with discrete random variables, I can talk about these probabilities, but in general, these are going to be PDFs. Okay, they're going to be the probability density functions, and that means that I can't actually write the probability in these equations. I have to use these PDFs instead. And so typically this is written with these functions which stand for these PDFs, and I'll write. I can use the same notation, but instead of writing probability, think it's a function, and this will be one of these probability density functions. I'll use lowercase p for this probability. I'll use f, which is typically what I use for the PDF for this probability. This one is usually the most interesting. And then this one, they typically use pi. Okay, so in the lecture today, and maybe you'll see this in the homework or quiz or something, I'll try and make it clear about this, but I'll use these lowercase functions, and this is a, so like because of the technicality that it essentially can't say probability, because the probability of any given event is going to be 0 if we're talking about continuous random variables. Okay, and in general in this class, we're going to be thinking about continuous random variables. The lecture today and the homework will probably be mixed, and I'll explain why at the end of lecture today. When you're trying to actually solve this for the optimal one, there are some cases where there's a nice solution. If you remember at the end of class yesterday, we were solving just for this one. We're solving for the model which optimized this function, which we could write down, and it turned out it was an average. That's sometimes the case, which is nice, and sometimes it's not exactly an average, and we have to do something else. We'll talk about these later throughout the semester, some of these different cases. Okay, so these three terms are very common, and so they have names that typically come with them. This one is the prior. You've probably heard something, at least you've probably heard something at least like colloquially about kind of your prior knowledge about something. Your kind of prior about what you think the model is going to be like. That's into this function, and it's called the prior function. Okay, so we talked about the term likelihood. Okay, and so this PDF F is called the likelihood. Given a fixed model, I can usually write down exactly what the likelihood of seeing the data so the data that I saw. Okay, this one's often given to you in some nice form, and this one is often something you can calculate. Okay, and then this one is called the posterior. Okay, and I don't have a story about this name, but this is the one that we actually want to calculate. We want to find the maximum posterior estimate, or maximum a posterior, and so that incorporates both the likelihood and the prior together. Okay, if you just have a maximum likelihood estimate, it means you've kind of dropped the information about the prior, or you assume that it has no influence. You're just looking at this. If you find the maximum posterior estimate, the MAP estimate, maximum a posterior MAP estimate, that's the model which maximizes this, which is then the product of the likelihood and some prior knowledge there. Okay, so this was mainly something we've talked about the past lecture or so, but this is kind of, technically you should write it in this way if you're talking about continuous random variables. Okay, because these are PDFs instead of actually probabilities. You can think of them as probabilities. Sometimes I'll accidentally refer to them as probabilities, even if they're continuous random variables, but try and call them the likelihood or the posterior is usually the correct term, and refers to these PDFs. But in your mind, you can think probability. So let's go through an example here. So let's say that we're looking at an estimate that we're again given some data, x1, x2, up to xn, and these are the heights of, say, so students, right? So let's say I'm trying to estimate the average height of a student at the University of Utah. right? And so what I did is I measured all of your heights in this class, and I used that to try and estimate the height of the average student at the whole university, right? So these could be height values here. Okay, so let's say that I have a prior though, right? That I read some study online, right? That I think the model of the average height is a normal distribution of 66 inches with a standard deviation of 6 inches. I read this from some national survey about the heights of people and the age group of people at, typically at universities, right? So this would be the model, and so if this is a normal distribution, right? So a normal distribution is 1 over square root pi 72. That's square root 2 times the standard deviation squared under the square root. This is the right normalizing term just so it integrates to 1. Times e to the power. Remember, x is e to the power. It's e more. There's less ambiguity if I'm writing on the board. And so then this is, I'm estimating the model, or let's write that there's some mean here, minus 66, which is the prior here, divided by 2 times 6 squared. Okay. So this is a PDF. So this should integrate to 1 over all possible values. So mu of m as a possible kind of average height, right? And I said the mean is 66 inches, and the standard deviation is going to be 6 inches. So I read that this is it. So this would be like 5 feet 6 inches with a standard deviation of 6 inches. Maybe this is the population of the.
What's that symbol in the exponent?
Yeah. So this is a mu of m. Mu, if you're writing this inside LaTeX, and so often you represent the mean of a distribution as mu. Okay. So I'm trying to estimate the average height. Okay. Good. So now I have data and mu, okay? So now I can say that, so now I have prior information as well, okay? So now if I want to estimate the posterior, okay, given this data, P of m, this is the so this is the posterior, then I can use some likelihood of the data, so given the model, times pi. So times pi of n. Okay, so now I can take the product of these two things, and we derive something that could work as this FD, so given m in the lecture last week.
Is the posterior represented by a P, or do you write it as a
It's supposed to be a P. Okay. Yeah, it looks a lot like a row, but this is a P. So it's a lowercase p. Yeah.
Sorry, where did the 72 come from?
Yeah, so this is the normal distribution. So sigma of x is going to be 1 over square root 2 pi sigma squared times x minus mu squared over 2 sigma squared. Right, so this is the normal distribution in general. And so the 72 was 6 squared, which is 36, times 2. Gives me 72.
Thank you.
Yeah. So, and then in general, you know, if you want to write down a PDF, you need to worry about this coefficient correctly so it integrates to 1. But I'm going to maximize this, so if this can go into this alpha, this proportional thing. There's some constant here. This will get absorbed into that constant. So don't worry about it too much. I just wanted to write it out explicitly in this case. Okay, so before we go through a little bit more math, let's say I just calculated this, and I took the average over this data, and I got back the answer 5.5. I think the answer or let's say 5.6. Okay, so I think the data I gave you on so last week, if I took the average of that, I get back so like 5.6. What should you do before you do any more calculations? Just looking at this. What's strange here? Yeah.
You should check units possibly, because it doesn't really make sense that you're getting average for your data set of 5.6 when your values need to be distributed with 66. So that seems to suggest you do one in inches and the other in
Yeah, that's right. Right. So the first thing to do with the prior is to kind of look at, does things it's like, are things making sense? Before you do any kind of actual deep calculations, you should use it as like a sanity check. Okay, the prior was 66 inches up here, right? And now, but my data is actually 5.6. You're probably not, average height is probably not 5.6 inches. You'd be this tall. So that's probably not the right answer. So a common issue, so it's like units. If I'd measured this in feet instead of inches, right, then I should have actually multiplied this by 12. If I multiply this by 12, I get something much closer to 66 here. Okay, and that's a more likely thing, right? So just as like if you take a class in like physics, the units are very important. When doing data analysis, the units are very important. Some big disasters have happened because people use the wrong units in different units in different parts of the analysis. Okay, so make sure the units match. Just do a sanity check between the likelihood units or the data units and the units on the prior. Okay, so good. So that you do before you do any sort of like any sort of calculations. Okay. Yeah. So if you just blindly put this in, you're going to still output a number, right? If I have this average and I go through the calculations, and I'll do something like this next, and I use 5.6 in here, I'll get some answer which is maybe so it was like 20, right? And 20 inches or 20 feet is no way the right number. It's going to be somewhere in between 5.6 and 66, and that's not going to make sense, but it will give you a number, right? So you can't just trust these numbers blindly. You should actually think about them. Okay, it's a lot of times people just trust them blindly, and it leads to some weird stuff happening. It's worth just stop and think. And this is one of those places that it's easy to kind of do this check. Okay. All right, so let's continue this example, right? And so I'm gonna so if you remember, let's write down what we had kind of gotten for this likelihood function. F of d, so given m. Okay, and so this was basically going to be a product right? So this is kind of like the sum symbol, but when you're combined together, multiplying a bunch of terms instead, looks kind of like an uppercase pi. Okay, so a product of this normal distribution now centered around these data points. And so let's say it's centered around the ith data point. So this was centered around actually the mean of the model. And let's say I assume now that that your measurement was a different standard deviation of 2 inches instead. Okay, so let's just put in number 2. We'll see what happens with this 2. Okay, so this is the product of xi and d, and if we assume that so they're independent, so with Gaussian noise of the true mean of the model, and so this is 1 over square root of pi 8, right? The 8 now comes from 2 squared, which is 4 times 2. That's why I get the 8, right? X of minus, turns out 1 over 8, mu of m minus xi squared. Right, so if I assume Gaussian noise with a standard deviation of 2 for each of the readings, then so this is what I get. Okay, and we have the prior derived from over here. So now the posterior, right, which is what I'm really after, is the probability of the model. So given the data and incorporating the prior, is going to be f of d given m, the likelihood, times the prior, right? So this is going to be and now I'm going to drop these coefficients here. And this is all right. So now just combine these together. I can do this, and if I want to do the log, then this is I can turn the product into a sum. There's a minus sign in front. I'm pulling out from all of these terms, and this is going to be plus all right, because I took the log of the exponents, right? So now the maximum posterior, the log of the maximum posterior estimate, right? Is the negative of the sum of these. So the minimum of this would be just ignoring the minus sign. The minimum negative log posterior estimate is going to be the one that minimizes this sum here. Okay, so if the prior has this nice form that I assume that it's Gaussian noise, so I have an exponential model, which is not uncommon, then the log posterior I can combine that together with the noise. I assume that the students were drawn from all of your heights were drawn from some mean with some noise model also. Okay. Okay. So there are a few things going on here. first I want to point out an issue with the assumption here. So this is from, so this is the heights of students, say, in class. Okay, so there's something broken about this. If I just chose all of your heights as a representation of the university's heights. What's broken about this? There are a couple things broken, and some of them we're fixing with the prior, and others we're not quite fixing.
Can you repeat that again, or what you're looking for?
Yeah, so okay, so I've written down the likelihood in this way, and in the class last week, I told you something about the data, which was important, so that I could write down the likelihood as a product here. Now I'm telling you that these data points are drawn from the heights of all of you guys measured in the class. This is supposed to represent the average height of a student on campus. Right? We're trying to derive that. Yeah?
Or you're just talking about you can't assume that the heights of people in this class are representative of the sample necessarily. Like you'd say computer sciences are going to be shorter than other majors.
So yeah, right. So this is the only issue, but one of the issues is that you're maybe not a representative campus sample of like all of campus, right? It could be, one issue is that in computer science there are more males in the population than females than on campus, and males tend to be taller. So this is probably not a good estimate. Okay, and so because of this bias in this estimate, we're trying to counteract that with the prior. So one of the points of the prior is saying we know something about the overall average. We don't know what bias is in this sample. So we're going to try and kind of use the prior to kind of go back to some more general knowledge, which is not specific to our university, but kind of was done in a way we hope does not have these biases in it. Right? So that's one of the issues. And the prior is designed to help out with these sort of issues.
But isn't there also the issue of, even with the prior, isn't there the issue that we have one statistical distribution that describes the data set for the students we sampled, for example, computer science majors, but in reality there could be another statistical distribution that describes all of the students in the university, all of the heights of these students in the university. So we have that issue that there's a disconnect necessarily, even with prior information, but it may not exist in reasoning completely.
Yeah, so what's going on here, and this is part of the same issue, is that there are three so distributions. Okay, so there's all university students, say, in the U.S. And so we assume that this was used through some big study somehow to tell something about the prior. Okay? So then there's students in CS and actually in CS. So actually students at 3190, right? And this gives us a different distribution. It's a subset of this one, right? And then our goal is actually, but the goal here is students at U of U, okay? So maybe if instead this was a random like intro class that everyone had to take, then this would be probably a pretty good estimate of the students at the U. Okay, because it's a random sampling of the students at the university, but there might be some bias in there. It could be that there's, even in these classes everyone has to take, there's some variation in year and other sort of things. Maybe people are getting taller. Every year the students are getting taller, and so if it's a freshman class, because there are seniors who are on average shorter, then this is not a perfect estimator. There's some bias in between here, but we're hoping that these two are closer than this for the whole university, than all university students. Okay, so that's kind of the hope in this modeling. I'm getting a sample of hopefully representative students to estimate this, but I'm using this as a prior, and for one, it can tell me if my units are wrong. If I'm way off, then something is amiss. But it can also help prevent against, in case there's a bias here, it'll hopefully draw me back towards something more reasonable in that case.
So it's like our output essentially suggests we're looking for a mean and standard deviation for the students in the University of Utah. Is that like what we're looking for?
Yeah, what we're looking for is only the mean. We're just looking for the average. Yeah. There's still something else wrong about this, and it has to do about this product, right? I took this product. Yeah? Yes. Yeah. So in order to write down the likelihood as the product, I had to assume that the data points were drawn independently from the distribution. Although if I can't assume independence allowed me to say that their joint probability was the product of their individual probabilities, or their joint likelihood is the product of their individual likelihoods. If I don't have independence, I can't necessarily do this. Okay? And what independence would mean is that every sample I drew here, I basically took someone's ID number and I sampled it. And the next one, I did that same process over again, and I could have sampled someone twice. Okay, so I had the possibility of sampling someone twice instead of, whereas with the whole class, what's happening is I'm not sampling any of you twice, right? I know that I'm sampling you, so basically without replacement. Right, so I can't sample anything twice, so they're not quite independent. Okay. So it turns out, in general in estimations, this is not actually a problem. It's what happens when you sample stuff without replacement. So say a fixed set of people and not sampling anyone twice. Then things have what's called negative dependence, and you can probably use this estimator without any issue. On a small sample size, you're about 60 students out of 10,000 students that you use, something like that. So the probability of sampling someone twice is pretty small. So that this probably is not an issue, but you should pay attention to this. This is technically not correct if I just sample students from the class. Whereas if I sampled random ID numbers and got their height and could do it with replacement, then that would be fine. So just there's a couple of small lies going on here, but this is common. Yeah.
So if you just had a class, would it be better to sample with replacement from that single class? Or would it be better to just get everybody's height from that class?
It's going to be slightly better to get everyone's height from the class, actually, and not do independent. We'll talk about how, getting a sense of the variance of this, that'll be in the next two lectures. Not quite the variance, but other sort of bounds on how accurate this is, how much concentration. And it turns out negative dependence is better than dependence in terms of concentration. Not much better, but slightly better. If the sample size gets very large, like I'm sampling half of all students at the university, the ones currently on campus at this moment, something like that, then it's going to start to get noticeably better if I do without replacement. I just count everyone instead of random sampling. Okay, good. All right, so there are a couple of small issues going on here, but But so really nothing major. At this point, it's safe to kind of step through these calculations. Okay, so the next thing is that I've written down this log posterior, and I want to maximize this negative log or maximize the log posterior, or minimize the negative log posterior. So posterior, so if I put the minus sign over here, then I want to minimize this term. Okay, and we said before that if I just had this part, right, then this was just an average, right? But I had this 1/8, but that was the same everywhere, so I could factor that out. Now I've got a 1/8 here and a 1/72 here, right? So this 1/8 here is different than this. Okay, so from a technical perspective, it's going to turn out, and if we have time towards the end of the lecture, I'll actually go through the derivation of this, but that the result is going to be a weighted average instead of an average. So I can still calculate this instead. So a weighted average, okay, so you've probably seen something like this before, but I'm going to have a set x1, x2, up to xn, and each of these are going to have these weights. Okay, in this case, I'm going to have a bunch of data points with weight 1/8, and then this prior, which is going to have 66, which is going to have a weight of 1/72, right? So, or basically, this can be a weight of 1, and this can be a weight of 9. Right? I can do that the same way. Think of these as, or sorry, if I can put this as 9 and this as 1, right? So these are weighted by 9, this is weighted by 1. Okay, and so then the weighted average here is similar to the average. It's going to be the weight times the value divided by just the weights. Okay, so every data point corresponds with the weight, and so this is just the weighted average. And if I plug in either a 9 or a 1 here in the appropriate spots, then this gives me the right solution instead. So I can just do a weighted average here. It means that, so to interpret this, it means that each student in the class, how I've set this up, is given 9 times as much weight as the prior. Right? Each student has the same weight towards contributing toward my estimate, but the prior is given 1/9 as much weight. Okay, and this difference stems from the choice of the noise model here. I took 6 inches as a standard deviation here, and here I said that this was a 2. Yeah, a 2 here. Right, so this was 2 inches on what I assumed was your noise model. Okay. And so because this one has more kind of uncertainty to it in how I set this up, it's given less influence here. What's the difference? Why do I get a factor of 9? Because these are off by a factor of 3. And it turns out that this is the squared quantity I'm looking at, so I've squared 9. I've squared 3 to get 9. If you go through the math, that's what's going to wind up. So if this was an 8 instead here, then it would be a factor of 16. That'd be the factor 4 squared of 16. Okay, so did this make sense to give this a standard deviation of 6? And this is standard deviation of 2. Well, I erased this over here. But if I had instead, this would make sense if I said, well, I don't trust the prior that much. I really think the students in the class are pretty good representation. I don't trust the US data because, I know people at Utah in general are taller than the average population. right? So I'm not really gonna trust this that much, but I'll use it for some sanity checks over here, and then I just want to kind of do something here. But this really is not doing much, right? It's a fact. If I have one student, it's even just one student estimate is really going to dominate this. It's going to give it a fact. One student is 9 more. If I have 60 students, that's 60 times 9. What is that? That's about 550 times the effect of the single prime. Okay. And so what was going on here? I set this. I thought you had a noise model of 2 inches standard deviation. Maybe that's reasonable. And this was the population distribution. But really, I'm saying, how confident is this distribution here? And maybe I say, well, this was the population standard deviation, but my confidence in the standard deviation maybe is much smaller, right? So maybe I said that the standard deviation was actually 0.1 inches of my confidence in what this estimate was. Okay, so if this was 0.1 inches instead of 6 inches, because I'm much more confident that this is right. I've seen a lot of US data, so I trust this much more. Then if I go through this calculation, this becomes a 0.1 squared, which is 0.01, right? And I push this through here. This becomes a 0.02, and this ratio changes. This basically becomes a 1, and this basically becomes 400. So the difference now is this was a 2, and this was a 0.1, and the factor here is 20. That squared is 400. So now I say I trust the US population 400 times as much as a single student. Okay, so maybe this is more reasonable, right? I want to see if there's kind of some difference going on here, but I'm going to start of assuming I have 400 students worth of data. Maybe this was collected from 400 students prior to this, and I'm adding to it the students in the class. And maybe these are collected from the U, or maybe these are collected nationally, but I don't trust that they're the same distribution, so I'm going to downweight the 4,000 national students, but downweight them or by some factor. And kind of analyzing this, there's some statistical techniques of how to do this the right way, but sometimes it's kind of just you're modeling things. You're making a modeling decision.
So isn't the 6 the standard deviation? Or is 6 now?
Well, 6 is my prior, right? So that's saying that I'm trying to estimate some value in inches. And let's say 66. And so maybe I've measured the population, right? So I've measured a population, and it goes out to 72. Actually, this would, one standard deviation, 72 would be here, and 60 would be here. And this is what the population looks like. But if I've sampled like 10,000 people from this, I'm much more confident, and this is what next week we'll talk about, I'm much more confident that the true value is somewhere around here. I think the true value actually has a distribution that looks like this. It's really concentrated around 66. And this standard deviation is now 0.1. Because if I sampled 10,000 people and I took that average, I said, okay, I'm pretty confident that it's actually going to be here because I've seen so many data points.
But it's not the standard deviation of
It's the standard deviation of our prior understanding of what we think the average height is.
where the mean will fall, but not the standard deviation in difference in height for students or for people.
Yeah. So this was probably the wrong thing to do, unless we didn't trust it because we said there's difference in the population. So
Right.
I just factor it in here because I don't know where else to put it.
So this equation you've got at the bottom here, so this natural, negative natural log thing.
Yeah.
The other side of the proportionality, are both of just didn't know if it like broke off.
Oh, okay, good. So this summation looks like this. Good. Right, so this sum is over just these quantities, plus I'm adding this term. I've got a product over these guys, yes, and this product goes like this. Good. Thank you. So this is all the likelihood, and this is the prior. Great question. Thank you for helping.
So in the top part, where it says likelihood, there's the 1 over the square root of pi times 8. Where did that, and then the other term, for the prior?
This guy went into here. It's a constant factor. I can ignore it.
So for both the likelihood and the prior, it is kind of dark line there.
Yeah, so I'm using this notation, this proportional to notation, and I can drop constant coefficient. That's one of the powers of this notation, right? So one of the things about this class is introducing kind of this notation, and hopefully you appreciate that, I've introduced this because it allows me to be precise, but to drop this stuff that ultimately doesn't matter. So that's what I'm doing. Yeah.
And similarly, we could drop the 1/8 and build in summation, the 1/8 on the last line where you take the.
Well, I can't do that because this is a 1/8 and this is a 1/72. Now I can change them. I can multiply through by a factor 72, and then I get a 9 and a 1. Right? Or if this was actually, I started with 0.1 inches, then this would actually be like a factor of 50 or something, positive 50. So I'd have to divide through by 50 or something like that.
But there are instances where we could do that.
Yeah, for instance, the stuff we did last week, then I didn't have this term, and then the 1/8 could factor up.
Yeah.
And that's what I did. That's what I did last week. Now I need to combine these together. I need to use the weighted average to calculate instead of just the average. But it's not much harder, right? This is basically just as simple as the average. Okay, good. So okay, the other thing is, let's say that I did set this so that this distribution here was this really narrow distribution, so 0.1 inches. I really trusted this the population prior much more than the students in the class. But, so that means that if I have 60 students in the class, then this one is going to be, 6 to 7 times weighted more than all the students. Right, because there are 60 individual things here times one thing worth 400. But if the class grows, like let's say this gets really popular, next semester I have 1,000 students in the class, well then I'm going to trust the data I've collected as an aggregate more than the prior, even with this kind of really powerful prior. Okay, so as you get more and more data, eventually the prior should kind of wash out. And that's the point. As your data kind of keeps growing, then you don't need to trust your prior knowledge as much because I have a lot of data. Okay? And this is kind of one of the reasons why you often, even if you have some prior, you often drop this and just work with the likelihood, is in large data scenarios. So if you're dealing with big data, then it's often fine to drop the prior because you have enough data, assuming you trust that data. If you don't trust the data because it's from the wrong distribution, then you might want to bias it towards something you know with the prior. And this is kind of the proper mechanism for doing so. Okay. Okay, so what else did I want to say? So, okay, so there are a few other things, just to kind of wrap up Bayesian inference. There's kind of other things which we're generally not going to talk about in this class. There's a grad level class that kind of goes into a lot more about this, but so posterior is not a is like not a probability for if the model space is continuous, right? Because then I have a continuous random variable. It's a PDF instead. So that means I can't talk about probability, but I can still do certain things. It still acts like a it's a PDF, and so that means that I can do various things. I can take two of these things, and so I can compare them. So if I say the posterior of model 1 given the data divided by the posterior of model 2 given the data is equal to 2, right? Then this implies that model 1 is twice as probable as model 2. Okay, so I can still look at these ratios. This is not the log, the negative log posterior. This is the posterior, so I need to take the exponential first if I broke it down to a sum. But I can talk about the ratio of the probability. So I can talk about ratios between them. I can say something is twice as likely. Okay. I can also look at so I can get I can use a distribution of models to estimate. Okay, so let's say that there were 3 models, M1, M2, and M3. Okay, and so one option is I could say I can take the map estimate, and let's say the maximum a posterior estimate is going to be equal to M2, right? And then I have a so prediction I want to do, and so we'll talk about prediction a bit more. But I say I have a new student coming into the class, and I want to estimate what their height is going to be, for instance, something silly like that for the examples we have now. One option is I can do I can just use M2 of the data, but the other is I can do a kind of weighted estimate over these. Okay, the same way I did a weighted average, if I have posterior probabilities for a fixed set of models, or a PDF over continuous that I would integrate instead. But let's say that I have the probability of M1 given the data is going to be 0.4. The probability of M2 given the data equals 0.5. This is the map estimate. And probability of M3 given the data is going to be 0.1. Okay, and then let's say that what I want to do is to predict the average squared height, like in some, I guess in some animals, like squared height is proportional to weight or something like that. This is a slightly more interesting example. And let's say M1 equals 1, M2 equals 2, M3 equals 3. And I wanted to estimate the squared height. So my map estimate, so this would just be the map estimate, but I can do this distributional estimate. I think green's not going to show up very well, so let me switch back to black. The map estimate, or the map estimate would be 4. It'd be the squared height, right? So but I can do a weighted estimate of the square of the model. This would be 0.4 times M1 plus 0.5, say squared, plus M2 squared plus 0.1 times M3 3 squared divided by 0.1 plus 0.4 plus 0.5. It turns out if these were probabilities, then this equals 1, and I can kind of ignore this denominator. Okay? And so that'd be 0.4 times 1 plus 0.5 times 4, that's 2 squared, plus 0.1 times 9, that's 3 squared. And so this turns out to be something like, say, 5.5. Right, so I'm going to get, even though there was only a 10% estimate probability of being this third model, but this pulled it to be larger. Okay, so I can get this weighted estimate of the squared model, and sometimes this gives me a better estimate than just using the maximum a posteriori. Instead of using the mode of a distribution, you're using the kind of the average of a distribution. I think that from a statistical kind of statistics point of view, that's a comparison between these two. And so this is often more robust. Usually, and what we'll do in this class, this is going to be more difficult because we're going to look over a continuous space of models instead of a discrete space of models. So instead of just doing adding, this would have to be integral, and this is often pretty more challenging to do, and we usually aren't going to do this. Okay, but you could do something like this. And for simpler estimates, where you have a smaller set of models, this is often a good thing to do. The other thing I can do is something like a confidence intervals, which is related to hypothesis testing in ways we're not going to get into. But I can say, let's say I have a continuous space of models, and I can say that, for instance, I can say all models M, say, in between 0.5 and say 3.5 have a would have so I could say the integral. So this is some range, and if I integrated the models in this range of the posterior of the model given data, I can say that this is less than or equal to 0.95. I can do something like this, and this is saying that with 95% probability, the model will be between 0.5 and 3.5. Right, that the right value of the model is. So I can start to write down actual probabilities, and this is kind of like related to these hypothesis testing, where you want to be 95% kind of confidence that something is true. Say with 95% confidence, the model is in here. Right? If the integral of this is kind of is bounded by here, then I can say 95% confidence. Right? So I can talk about probability even though it's not specifically a probability. Okay, so you can, there's a whole bunch of, and sometimes, and especially for continuous models, this sort of stuff is more powerful, but it's more difficult to do, and there's a lot more in this direction as well. Okay, good. So let me, one more thing I was interested in doing, but it's not as important as if you have questions, but I was going to derive that this is minimized by the average. It's a question from this. Okay. Let's do it over here. Okay, and just for simplicity, let's do the version that's not weighted. So I want to find the min over all choices of a model in the real numbers of the sum of xi in some data set of xi minus this model value squared. And I want to derive that this is going to be the average of these values. Okay, and so it turns out that it's not too hard to derive this. I can expand this to be xi squared minus 2m xi plus mi squared. That's just expanding the sum. Expanding the product before I take the sum. And this is equal to xi squared minus 2m, just the sum of the squared terms, minus 2m times the sum of the terms, plus, let's say, the size of the data times m squared. Okay. Once I have it in this form, it's easy to say, we're going to write this as sum of squared error of d given this model parameter. So I can write the derivative with respect to m. Right, so I can write the first derivative of this with respect to m. This term goes away. This is 2 times this sum of these items, and this term is plus 2 times m. So, okay, and if you remember that the minimum or the maximum is going to occur where the first derivative is equal to 0. So if I set this equal to 0, now I can solve for m. Right? I can say m is going to be equal to 2 sum of xi and d divided by 2 times the size of d, and the 2 cancel, and this is exactly the average of d. Okay? So by just expanding, taking the first derivative with respect to m, the minimum or the maximum has to occur at m equals the average of d. The sum of the terms divided by the number of terms. Okay, and is it a minimum or a maximum? Well, if the second derivative is positive, it's a minimum. If the second derivative, this term goes away, and this term has an m left, and it's 2 times the quantity is always positive. So it has to be a minimum. Okay, so that's why the sum of squared error terms is minimized at the average. And this will come up. We'll use sum of squared error kind of all over the place, and it equates to an average, which is a kind of very sensible way to do an estimate. Okay, so this was all I had planned for this section of the class. I can answer any questions that we have about this, about any of this material, or as next week we'll start talking about concentration of material.
What does SSE subscripted stand for again?
Yeah, so well, it's exactly this, right? So this is sum of squared error. Yeah, so there's also mean squared error, is where I divide this through by the number of things I have. But that's the coefficient, it's minimized at the same spot. So they're the same minimizer. People often, the mean squared error is more interpretable. because it's the average squared error. The root mean squared error, RMSE, is the square root of the mean of the squared errors, and that has the same units as the data itself. So the root mean squared error, RMSE, is going to be the square root of 1 over d times the sum of xi in d of xi minus some estimator squared. Right? So the root mean squared error. And so this is an interpretable quantity, but they have the same minimizer as just the sum of the squared errors. They're minimized at the same point because this term is always positive, so I can always take a square root, and otherwise these are monotonic functions.
So after that, all we did was we took the derivative of the sum of the squared error, and then we set that equal to 0. And that just tells us where that minimum is at, is where that value is 0.
Yeah. So a nice thing about this, right, the sum of squared errors, if I look at a function of m on this axis, and this axis is the sum of squared errors, right, it's going to look like a parabola. Okay? It's a sum of parabolas. The sum of parabolas is a parabola. It's going to have a minimum point. Right? This is where the derivative is 0.
Oh, okay.
Yeah? And the second derivative is positive. That means it's a minimum. Right? Yeah, so this is important. And so basically the more data points you have, the sharper it's going to get. Because you're adding up parabolas that have, each of them might look kind of fat by itself, but when you stack them and they're not all the same center, then they're going to kind of get more and more narrow. And that means that essentially it's going to correspond with an estimate getting better and better. And this will kind of like that will be the next 2 lectures we'll be talking about how to understand your estimates getting better and better. And it's going to get better as the number of data points n grows with us. It's going to get, as the square root of the number of data points, that's going to linearly decrease my variance, and that's going to be one way of thinking about this. And so we'll see. A cool thing to keep this picture in mind, we'll talk about higher dimensional estimates later on in this semester. We're estimating a quantity which is not just a scalar value, but a higher dimensional point. And one weird thing to think about, if you like this picture, is that each of the data points is going to kind of give you this tube that's a parabola in one dimension. It's going to kind of be a parabola coming on the board. But each of the data points is going to have the half pipe, whatever, going in a different direction. Right? So each of them by itself is not going to be kind of what's called strongly convex. It'll have a flat spot at the bottom. But when I put a bunch of them together and add them up, then there's going to be a single kind of parabolic shape. So if you kind of like this way of thinking, when you stack more of these together, we'll see this. We'll think about this later in the semester. And that'll be important for ensuring that there's actually a optimal solution. Yep.
So I'm still kind of like lost on this likelihood function that we're not supposed to take the product of because we can't say they're independent.
Yeah.
So like how did this likelihood product or this likelihood function come into existence in the first place?
Right. Okay, so if you remember, we could write down was exactly this noise model, which was exactly this normal function. This was mu of m2 of xi, which was some coefficient right? So for one point, we assumed it was drawn from a Gaussian distribution or a normal distribution with mean mu m and some standard deviation. Okay, and so that means given this model, that's what it's saying here, conditioned on this model, we assumed that it was drawn from mu m with the standard deviation here. So that means that the noise model looks sort of like this. And so it was twice as likely. So kind of a way of interpreting this is that these two values, it's twice as likely to have this value as it had this value, because the height function is twice as tall here as here. And so I kind of assumed this about the noise with the standard deviation, say of 2 or whatever it is. Okay, and so let's say I assume this model, and then I see one data point here, and the likelihood of this data point is measured by the height of this red line. That's this value here. Okay, but this would be x1. Let's say I also saw x2, which had this likelihood under this model, and I also had x3, which had this likelihood. Okay, and so I've got a bunch of data points, and then I want to say what's the likelihood of this single model being that I made all of these observations. Now, if I assume that they were independent, I could write down the likelihood for each one of them, and then I know the joint likelihood is the product of the individual likelihood of independent random variables. And so if I assume they're independent random variables, I say the joint likelihood d given m is equal to the product of xi given this model. And this is, the single one is written down here. And so you can think of, and then I eventually want to find the model which maximizes this one without any prior knowledge, without any prior, it's going to be, think of the average of these points is going to be the thing that, if I take the product of all these heights, that the center point which maximizes the product of the heights is going to be the average of those points, as it turns out, kind of magically through this algorithm. But does that refresh you how to get the product of these?
Yeah, I got that. It just seems like you're just going to be like extremely, if you're just multiplying fractions together, then you're just going to get extremely small values for this likelihood function. And that's what you're supposed to get, basically?
Yeah, right. So keep in mind that, the true probability of the model is not the posterior, but is normalized by the probability of the data. Right, so it's a really small value, but the true model may actually be in a pretty narrow range. And that's kind of maybe what happened here, right? I got data all over the place, but there's a PDF of the model which actually is fairly concentrated. Because if I normalize it properly, then that's true. But it's a really small value, but that value does not have an intrinsic interpretation as probability. It's a PDF in a weird way. And I don't actually want to calculate those really small values. I want to just take the log posterior, and then I have a sum. And these are much more stable to calculate. Yeah, so it's a good point, but it turns out there are kind of two ways that it becomes not really a problem. So great. So I'll see you next week on Monday. I guess the lack of cooling is starting to kick in here. Great.